A wave is a disturbance that transports energy from its source to another location without transporting matter. The frequency f is the number of complete oscillations made in 1 second. It is measured in hertz. The amplitude A is the maximum displacement in either direction from the equilibrium position. The wavelength lambda of a wave train is the distance between two successive particles which are at exactly the same point in their paths at the same time and are moving in the same direction. The particles in a wave train which are one wavelength apart and move in step with each other are said to be in phase with each other. Waves can be classified as either mechanical waves or electromagnetic waves. Mechanical waves require a medium. Those can also be further subclassified as either longitudinal waves or transverse waves. An example of a longitudinal wave is a sound wave. An example of a transverse wave is a water wave. Electromagnetic waves which do not require a medium can be broken down into many different parts such as light, microwaves, infrared, X-rays, ultraviolet rays, and radio waves. Let's compare transverse and longitudinal. In a transverse wave, when the wave is going forward, its particles are moving perpendicular to it, in other words, up and down. With a longitudinal wave, when the wave is moving forward, its particles are moving back and forth, in other words, parallel to the wave. A transverse wave is characterized by its crests and troughs. The crest is the highest point on the wave and the trough is the lowest point on the wave. Longitudinal waves are characterized by their compressions and rarefactions. The compression is where the particles get squished together and the rarefactions are where they are more spread out.
This is where the particles vibrate parallel to the direction in which the wave of energy is travelling. Notice that the ends of the slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions. An example of longitudinal waves is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on until the vibration reaches the ear, causing the eardrum to vibrate. The vibrating air speeds away from the source, creating a sound wave. Let's look at another type of wave, transverse waves. The hand moves up and down, as does the slinky, but the wave itself moves from left to right, so the particles vibrate at 90 degrees to the direction that the energy is moving. We can simply think of it as, in longitudinal waves, the hand pulses horizontally, pushing and pulling, and the wave energy also moves horizontally, back and forward. Whereas in transverse waves, the hand moves up and down, but the wave energy still moves horizontally. Again, the ends of the slinky never leave the hands holding it. It's just the energy that moves along.
Let's look at an example. The displacement time graph below shows a wave traveling across water at a particular place with a velocity of 2.0 centimeters per second as shown. Let's answer these 4 parts to the question. Part A, amplitude. We determine the amplitude by looking at the crest and seeing what displacement value corresponds to the crest. From our graph here, it is 2 millimeters. Converting that to meters, we divide by 1000 and it gives us 0.002 meters. Part B, the period. The period is the time it takes for one complete oscillation. So as we can see here, starting from the origin, going up to the crest, back down to the trough, and again to the origin takes 0.2 seconds. Part C, frequency. If we know the period is 0.2 seconds, then the frequency will be 1 over the period. So F will be 1 divided by 0.2 seconds, which gives us 5 Hertz. Part D, wavelength. At this point in time, we have the frequency is 5 Hertz and as stated in the problem, the velocity is 2.0 centimeters per second. If we rearrange the formula v equals f lambda, we have that the wavelength lambda is equal to the velocity v divided by the frequency f. Substituting our values, 2 divided by 5 gives us 0.4 centimeters. Dividing by 100, converting it to meters, we get 0.004 meters. In summary, waves can be classified as either mechanical or electromagnetic, and the particles of transverse wave move perpendicular to the wave motion and longitudinal waves move parallel to the wave motion.